Today in Applied Science, I'd like to show you this X-ray fluorescence gun. Not only does this thing look like a sci-fi prop, it actually works like one too. You just aim it at something and pull the trigger, and it even makes this fanciful kind of ray gun noise. And what's happening is it's emitting X-rays and then examining the reflection from the metal there. And after 10 seconds, it's captured enough of these reflected X-rays, and it gives us a complete chemical breakdown of what it was just looking at, down to a fraction of a percent. And then it uses all of this information to figure out what the metal alloy is with very high accuracy. So you can see here, this is stainless steel 304. And it even measures things down to hundredths of a percent level, so molybdenum 0.03% even. So in today's video, I'm going to talk about how this thing works, some different tricks you can do with it. I actually learned quite a few things about X-ray fluorescence that I didn't know before. And then I have an identical model to this gun that doesn't work. And so we're going to do a teardown on this one and a failure analysis. And you'll see there's a really unusual power supply design. And then I have a funny story about trying to buy one of these on eBay and being rejected by the seller once he found out that I was going to show it on YouTube. So let's see how these things work. Let's talk about what this machine actually emits. It's true that you wouldn't want to turn this on and take a nap next to it because it does emit X-rays. But to put this in perspective, this is about 10 or 100,000 times less powerful than a typical medical imaging X-ray tube. So I've covered up this proximity sensor on the end here so that this thing will emit X-rays even when it's not butted up against an object. And I'm going to aim it at my mighty ohm Geiger counter there. So you can see it does trigger the Geiger counter, but it's actually not as intense as even some radiation check samples that you can get. This software is configured to emit 7 microamps at 40 kilovolts. So again, that's 10 or 100,000 times less than a medical imaging tube. I'm going to try to set this up in a dark box here with a fluorescent screen so you can get a sense of how big the X-ray spot is. Okay, so X-rays are emitted by this thing, but then what happens? How does it work? Well, if we aim these X-rays at some material that's made of atoms, here's the nucleus with neutrons and protons, and we've got electron shells going around. The old-fashioned way of naming these shells is KLM, but this is the same as 1, 2, 3. It's just that the X-ray field, for some reason, uses this older notation. And then within each of these shells, there's the SPD orbitals and stuff, but that's not going to matter for today's discussion. So we've got this, neutrally charged atom with the same number of electrons distributed through these shells as there are protons in the nucleus, and everything's fine. But what happens is, when we come in with an X-ray, remember, photons don't have mass, but they do have momentum. And so when one of these photons, just by chance, hits one of these electrons in just the right way, it actually knocks the electron clean out of the atom. And this leaves it in a very unstable state. So immediately one of the other electrons from somewhere else in the shells will drop down to this lower level. And when this happens, it's going from a kind of a weakly bound state to a very tightly bound state. And when this transition happens, it emits another X-ray in return. So it's a cool process where we get X-rays in and then X-rays out interacting with the matter. Now the really clever part is that the amount of attraction that this inner electron feels is proportional to the amount of charge in the nucleus. So you can see how this thing was able to identify chemical elements. We have a photon coming in that could be a lot of different energies, knocks the electron out, this other electron comes down to here, and then the amount of X-ray energy that's coming back is proportional to the number of protons in here. In other words, the atomic number of that element. So we know exactly what element it is. You can see there might be a few variations here. The electron could come from this outer M shell, or it could come from the L shell. And so there might be 2 distinct energies that come out. And this is, you'll see this later, the peaks are known as K alpha or K gamma. And that's just basically different energies coming out from different electrons replacing this knocked out electron. But the point is that you get this fingerprint of X-ray energies based on what atom it is. Another cool factor is that this inner electron shell is very heavily influenced by the nucleus, but it is not influenced by other chemical bonding that's going on very far outside the atom. So this atom could be in a chemical compound, it could be in an alloy, it could be anywhere, and this technique really only focuses on atomic numbers. So you have this really like direct line path toward figuring out what chemical you're dealing with this X-ray fluorescence technique. One of the burning questions that I had when researching this is why, when you excite something with ultraviolet light, the color emitted is not dependent on the atomic number. So if we look at the periodic table here, I just said that if we do this X-ray fluorescence technique, the elements that are very low in atomic number emit very little X-ray energy. And as we move down the chart, every one of these elements will have more and more X-ray fluorescence energy. And that's true because of this relationship with the nucleus. Now, when we excite something with ultraviolet light or with electrons, we're really only exciting this outer electron. And this might have an energy value to knock one of these other outer electrons out could be, 5 electron volts or something, not very much. And when we do that, this outer electron doesn't really feel very much of the attraction from the nucleus because it's shielded by all these other shells of electrons in here. So this 5 electron volt, needed to get one of these outer electrons out is very not influenced by the atomic number. In fact, almost not at all. So when we look at the chart, at first it seems almost like, well, if this was red, you'd expect green light here and then blue light down here. But it ends up not working that way. In fact, the atomic number has almost nothing to do with the energy needed to kick one of these outer electrons out. If one of these outer electron volts only requires 5 electron volts, that places it, in the blue light or the ultraviolet range. One of these inner electrons requires, tens of thousands of electron volts, which puts it into the X-ray range. And so the reason that we need X-rays to do this molecular probing sort of thing to figure out what the atomic number is just because these inner electrons are so tightly bound, it requires these tens of thousands of electron volts of energy to knock one out. You can see that there's actually another limitation here. If the returning energy is so low that it is absorbed by everything that's between our detector and the thing that's emitting it, then we can't effectively detect it. And this ends up being a really big practical problem. So if we're inputting energy at 40 kilovolts, right, because I said that the X-ray tube in here operates at 40 kilovolts. So let's just say it's a 40 kilo electron volt photon going in. If our return is only 500 electron volts, let's say, it's a very, very weak X-ray. It's possible that even the air and the construction materials of the detector itself would absorb that photon and we can't detect it. So this gun is not a particularly new model. And it's only able to detect things that are heavier than somewhere around titanium. So if you're looking at a sample of aluminum, the gun actually does not detect the aluminum at all, but it can sometimes tell you what alloy you're looking at based on the trace element analysis, but it actually doesn't see aluminum. In fact, anything lighter than about titanium is essentially no signal. This could be good. I mean, if you ignore oxygen, that's fine because you may not care about oxygen in your sample. You're mostly interested in the base metals. But keep in mind that the heavier elements are easier to detect because they emit much more strong signals, and those strong signals penetrate all of the foils. Like, for example, the window on this thing is made of metal. It has this, shiny metal window. So the return X-rays have to make it back through that window, and that means they have to be more intense than at least a couple kilo electron volts, say. One of the biggest commercial uses for these guns is at metal scrap yards because they're so good at identifying alloys. So if you want to melt down a bunch of scrap, you have to know what you're putting into the furnace, and these are really good at figuring that out. But I found a couple other interesting applications. These are some glass samples that I made in a previous video. And if you recall that the way that we color the glass is by putting metal ions in there. So if you forget a recipe or you want to know what color is being produced by what ion, we can actually aim the gun at one of these glass samples and find out in just 10 seconds. The reason that it takes 10 seconds is because it's accumulating all of these return photons. And so remember I mentioned that you're putting in this high energy photon, an X-ray photon, and you're getting one back. If you're getting too many back at the same time, we can't measure the energy easily of each one. So actually, instead of just turning up the power on the X-ray tube, that wouldn't necessarily make our job much easier. What we need to do is basically set the power level low enough where we get back photons that are essentially separated in time so that we can measure the energy of each one of these photons that's coming back. So over the course of the 10-second measurement window, we might get, tens of thousands of these photons back that we're going to measure. And instead, if we got, tens of millions of these photons back, they would be overlapping with each other and it'd be too hard to pick out what's going on. So if we look at the screen, we can see that chromium, 0.2%, and that's right, chromium is what makes it green. If we did the same test for the blue one, we'd find out it's copper for that. Similarly, I had this naturally occurring piece of calcite, and this has a really cool phosphorescent quality to it, where if you aim a ultraviolet laser pointer at this, or actually a 405 nanometer laser pointer, it has this really cool glowing effect. And if you search around on the web, you'll find out that calcite by itself is not phosphorescent. There's actually an impurity in this naturally occurring crystal that causes it to have this property. So sure enough, I took the gun and analyzed this calcite sample, and as we see, it's actually manganese that makes it, that gives it this property of phosphorescence, tiny amount. I mentioned that the gun also works on compounds, and it even works on powders in a plastic container. So the plastic is thin enough and absorbs so little X-ray energy that we get a good signal even through this plastic container. And it's a white powder. We don't know what it is. So we'll wait for the machine to give us some information here. Let's take a look. And as we can see, yttrium, 96.8%. And as it turns out, yeah, it's yttrium oxide in here. And remember, the oxygen doesn't show up in our analysis because it's too light. So even though the oxygen atoms are in there and they are emitting an X-ray signal, that signal is either getting blocked even by the plastic itself, or the detector in this gun is just not sensitive enough to detect that weak X-ray signal from oxygen. Okay, let's see what's inside these magic devices that lets them work. I've already taken this one apart and taken all the screws out just so it's easy to pull apart. This first thing sticking out is just a heat pipe. The sensor that does all of this photon counting in the X-ray range is probably needing to be cooled. There's no external cooler in here, but I suspect there might be a Peltier junction inside the detector, which is going to heat up, pump the heat out into this outer metal thing. So then there's this funny heat pipe just to, get the heat out of there, and it actually transfers it up to this metal plate behind the computer. And then there's a snout here that just protects the stuff that's underneath it. I don't think that filter does much but keep dirt out. And remember, this is for the proximity sensor, so there's just an optical sensor in there. And unless there's something opaque pushed up against the front of this, it won't activate the X-ray tube. And then we can see that there's definitely two things going on here. This is the sensor, and this is the X-ray emitter side. And we can pull that off. And interestingly, inside here there's a little piece of metal. And I suspect that that is silver, pure silver metal, that little square of metal that's in there. And what happens is the X-rays come in from the tube at various different energy levels. And when they hit the silver emits a very specific energy level, so that the X-rays that end up coming out of that little aperture there are mostly caused by the silver, the line basically created by silver. You can see the detector is actually very small. In fact, it's self-contained entirely within this sort of typical looking semiconductor package. Of course, it has a window on the front, and that window, I'm sure, is very delicate. It's probably super thin metal to let in as many X-rays as possible. But there's nothing sort of hiding inside here. That really is a very small thing. And then on the other side, this is the X-ray tube, and it also just unplugs, if I can get a handle on it here. And there we are. So the X-ray tube is a traditional construction thing. I should point out that this pack here, actually here, let's open it up. It has this very funny expansion bellows here because this whole chamber was filled with oil. And so I had to use a syringe and suck out all that oil, which is messy and gets everywhere. But the reason that it's filled with oil is to prevent arcing. So remember, this is a 40 kilovolt power supply, and it's hard to contain 40 kilovolts, and the oil also makes a convenient heat sink so that all the stuff in there is cooled properly. So the X-ray tube slides through here and has this O-ring to seal the oil in and plugs into there. So let's zoom in on this power supply, which is kind of the most interesting bit of this whole device. This power supply is built using a bunch of diode and capacitor voltage multipliers. And so each one of these boards is basically wired up in series. And we start off at essentially ground potential here. And by the time we're over to this side, it should be about negative 40 kilovolts. What's weird here is how it gets power to each one of these voltage multiplier ladders. There's a toroid on each one of these boards, and that's sort of the supply of the low voltage. The challenge is that if you've got this voltage multiplier up here, let's say this is going from 30 to 40 kilovolts, how do you get your ground voltage in there? I mean, you need a transformer of some kind. And so this weird white thing is actually just a one-turn piece of copper with a big insulator on it, and it links together all of those toroids that are on these voltage multiplier boards. Kind of a weird design. And so there's one toroid on the bottom that energizes this single turn of copper wire, and then this single turn basically distributes power into all the little toroids that are on these boards as it works its way up in voltage. Kind of a weird topology. I've never really seen anything quite like that before. This thing has to deliver, like I say, 40 kilovolts at around 10 microamps, and so it's not a huge amount of current. Seems kind of like a weird way to build it, but whatever. Another strange design principle is that it actually is a negative 40 kilovolt supply. So typically, if you want to do an X-ray tube, the way that you make this work is you have to put a filament voltage on the bottom, and you would make this 0 volts, and then you would put plus 40 kilovolts over here, the anode. And the reason you'd want to do that is because you need to control the voltage going into the filament to control how much emission current you get. So the way that you operate an X-ray tube is to just put 40 kilovolts on it, and then measure how much current is going into the anode, and then raise the temperature of the filament until you get the emission current that you want. And typically you would have like an op-amp or a servo control loop, monitoring this. The reason that you'd want the anode to be at 40 kilovolts and the bottom to be at 0 volts is so that you can attach your filament control circuit, near ground. I mean, this is going to be 6 volts to control the filament, and it would be convenient to have all this stuff be at ground potential. But the designers of this device had a problem. The front of the tube has to be physically very close to the snout of this device, right? Like the front of the tube is right up in here, crammed up against all this other metal. So the requirement, it seemed like they decided the requirement was that the front had to be at 0 volts, which means the back of the tube has to be at negative 40 kilovolts, which means that all of the filament control circuitry also has to be at negative 40 kilovolts. This is getting to be a really challenging power supply. So then the designers put another one of these single-turn transfer transformers in here to control the filament remotely without having any galvanic connection with the rest of the circuit. So it's quite a complicated, confusing thing. I'm not sure it's entirely necessary, but it is very interesting to look at and has all kinds of interesting stuff. There's a couple other circuit boards outside the high voltage that does probably some of the filament monitoring. So there's potentially a way that this thing measures the amount of current going through the tube. It's probably this little purple wire that goes all the way back. So basically sense this wire, and when it gets up to 7 microamps, cut off the filament control voltage. And if it drops below 7 microamps, give it some more filament current, and that's how it regulates itself. I did actually find out what caused this whole thing to fail. So it doesn't emit X-rays. Like you pull the trigger and the red light comes on, so the circuit thinks it's emitting X-rays, but hold it up to the Geiger counter, no X-rays come out. So that pretty much narrows it down to either a bad power supply or a bad tube. And upon closer inspection, there's actually a nick in the glass envelope here. And when I first took this thing apart, I don't know if you can still see it, there was actually a few drops of oil in the tube. Yeah, you can see it right there. So that normally is supposed to be vacuum inside the X-ray tube, and a little bit of a crack there, probably due to some mechanical energy input into it, sucked in the oil, and that was the end of that X-ray tube. So I kind of thought about, maybe it might be somehow possible to fix that. Probably not. And so I think what I'm going to do is take the detector and use it in another project, since that's a pretty cool little device there. And I have a feeling that detector might come in quite interesting projects. So we'll close with a funny story about me being rejected on eBay. Years ago, there was a publication that showed if you unrolled tape like this in a vacuum, it produces X-rays. And I did a couple videos on this, and my results weren't super conclusive, but it is a real effect. The triboelectric charging right at the junction where the adhesive is getting ripped apart will transfer some charge. And then as the tape gets unrolled, it's basically like a Van de Graaff generator where you're physically separating the charge. And then eventually there's a breakdown. The charge slams into, equalizes itself out. On the order of 50 kilovolts can be, built up this way. And you end up with X-rays because now you've got a 50 kilovolt charge with some electrons flying off and making the X-rays for you. So the researchers that found this principle started a company to produce XRF guns based on this principle. And as we saw, the power supply is pretty complicated. So if you avoid the X-ray tube in the power supply, yeah, you might be able to build the guns for less money. So this company existed, and I don't think they went out of business, but they're kind of ceasing operations or something. But you can still find the guns on eBay. And I did, and I thought it'd be cool to do a teardown of this commercially produced tape unrolling X-ray XRF gun. So I found one for sale and contacted the seller and said, well, I'm not interested in the gun. I just want the cartridge. Like the tape unrolling doesn't work forever. So the gun has a cartridge that you put into it that has the tape mechanism inside. I wanted to buy just the cartridge because that's where the interesting bits are. And the seller asked what I was going to do with it if I had one of these guns and needed a replacement cartridge or whatever. And I said, no, I run a YouTube channel. I want to do a teardown and show how it works. It'd be pretty neat. And he absolutely flipped out and said, no, you can't do that. He was actually involved with the company and wants to get it going again and was, completely scared that I was going to give away all their secrets or something online. Now, mind you, this thing is patented and you can download the patent and read exactly how it works. And it's true that, the thing I was curious about was how do you not run out of tape in there? Is it like continuous loop or what? But as it turns out, there was a little bit of a pivot, and instead of actually unrolling tape inside the gun, it uses like a silicone pad that is stuck down to a metal target, and then it's pulled away suddenly. So it's basically like constantly adhesive and then ripping it off. So it's just a linear movement, just a solenoid or something inside there. But I thought it'd be pretty cool. Maybe if someone has one of these cartridges or kind of wants to buy one or something, we can tear it down and see how it works. Anyway, I hope you found that interesting. See you next time. Bye.